Hi, this is Glenn Dane. This is another quick video in the series we're doing on behalf of the LIFT Light Metals Institute and the ASM Materials Camp for Teachers. What I want to talk very briefly about, as briefly as I possibly can, are three essential materials properties. This is really mostly, I think, to guide you in other readings. This might get a little bit difficult at times, but should have the key ideas in it. So here's what a car has to do. We've talked about this before. It has to be safe, durable, lightweight, relatively quiet, handle well. And that turns into material properties. We want materials that are strong and stiff, where we're going to find out strength and stiffness are really different things. Corrosion resistance is important. We're not going to deal with that in this unit. Density is also really important. Density is the relationship between weight and mass. Not between weight and mass, but between volume and mass. And dense materials have a lot of mass per volume. Materials should also be low cost, that's obvious. And then we're not going to talk much about it, but low embodied energy. How much energy does it take to make the material? Something else we might be interested in if we're worried about overall global footprint, but we're going to put that off for another day. So again, materials properties are really the key to design. With all of this, we want to be quantitative. If you can do that, get the units into it, you're practically an engineer. I'm going to focus on three things. Density, which has units of grams per cubic centimeter usually. Stiffness, we defer that a minute. And strength. Strength has units of force per area. And if you put that in SI units, that's usually newtons per square meter. And Newton per square meter we often call a Pascal. Newton is a fairly small force. Remember, that's the force that a medieval apple might have on the earth from Newton's days. Square meter is a big thing. So 1 Pascal is a really, really small stress or pressure, so we often deal with millions of pascals, or MPa, megapascals. Stiffness is a relationship between stress and strain, and that also has basically stress units of megapascals or billions of pascals, gigapascals. And we'll make this a little bit clearer as we go, but I do want to focus on the units. So density, here's the key idea. You can take some material, aluminum, steel, balsa wood, magnesium, you name it, and you could measure the volume of this thing. You can also measure the mass of this thing, and you could put that onto a graph for a bunch of different blocks of the same material of different sizes. You find out that mass and volume scale the same way, and the slope of this thing is density. Density is always the universally the ratio between mass and volume, and therefore it has units of something like grams per cm squared, or maybe kilograms per meter cubed. These things should be cubed. Hopefully I did that before properly, right? Yeah, there I had it cubed. Did it right there. So, this is for one material. This might be what you end up getting for balsa, for example. This might be what you end up getting for aluminum. And this might be this might be what you end up getting for steel. And what's really important about this is material density. So if you have a given mass of material, say a kilogram of material, and keep that constant, what we can see is you get a lot more aluminum for a given mass than you do steel. And it turns out the density of aluminum is about 1/3 of that is steel. So you actually get 3 times as much aluminum at the same mass. That's why things like aluminum, balsa wood, magnesium are such great materials for lightweighting. You just get more of them for the same price, or for the same mass, I should say. So now let's get into mechanical properties. Stress we'll go through in a minute is force over area. We're going to give that call that S, and that has dimensions of force over area. Again, usually newtons per meter squared, which is a Pascal. And that force, you could see acting this way through something in simple tension. Here's your force that acts this way. The area that reacts through is this way. And it turns out most materials will break, for example, at the same stress. If it's twice the cross section, it'll also have about twice the failure force that's required. If you take that material and stretch it, we have a measure of the amount of stretch, and that's called strain. Strain, we give the unit E, and if we take this and put a force on it, we might stretch it out this way, move this out like this, and this change in length divided by this initial length is our strain. So strain is equal to the change in length divided by initial length. I'm going to define a couple more terms here. Yield strength is force over area at yield. Ultimate tensile strength is force over area at the maximum force. And a stress strain curve I'll define in the next slide. So here's what we can do if we do things in tension. And I'm not going to dwell on this very much, and there's lots of stuff on the web about this. You take and keep increasing the force, and this is the cross-sectional area A. This is the engineering stress, S, which is equal to force over area. And this is the engineering strain this way. If you take this thing and stretch it just like a rubber band, initially it's elastic, and it goes up and down along the same line. The slope of this line is E, the elastic modulus, and E is equal the change in force divided by the change in the change in stress divided by the change in strain. Okay, that's your elastic modulus. And that turns out to be a pretty good materials property. That's always about 30 million pounds per square inch in these units for steel, about a third of that for aluminum, so 30 million psi for steel, about 10 million psi for aluminum, for example. Those are pretty constant. And then this is your yield strength, and then this is your ultimate tensile strength. Well, in a classroom environment, you can almost never do something like this. There are ways of doing it, but it's difficult. But what is not so difficult to do is to take a regular old table and then take a cantilever beam, hold that on with a C-clamp like that, and you can put a little mass on this like this, and you can see that the thing will elastically deflect. And that elastic deflection depends on how stiff that material intrinsically is, what its Young's modulus is, E. So you can do is set this up, measure the deflection. The deflection scales with force, scales with L cubed, where L is the length, goes as 1 over E, where E is this modulus. It goes as 1 over width here, and it goes with 1 over T cubed. So if we go from steel to aluminum, and I make something that's the same weight, well, for something that's aluminum, it will be 3 times as thick, but it'll have about 1/3 the modulus, it turns out. It's just the way it works. So the modulus of aluminum is about 1/3 that of steel. The density of aluminum is also about 1/3 that of steel. So what would happen to the deflection if we go from from steel to aluminum? If we go to steel, from steel to aluminum, this drops by about 1/3, but this goes up. This is 3 times to the third, so it's 3, 9, 27 times the larger in that term. So the thing actually gets way stiffer if you make this out of aluminum versus steel. So aluminum is intrinsically stiffer, but because you get so much more of it, it behaves as if it's almost stiffer in something like bending. That's why we like to make aluminum trucks. That's why they can be actually lighter weight, quieter, all that kind of good stuff. Strength we can also measure with this. We can use a engineering stress, engineering strain diagram, get something like this. Again, modulus. We can measure where we start to get deflection. We can measure the peak load. and then things start to neck, they start to break, and it's difficult to do things in tension, but it's easy to do things, again, in cantilever bending. And again, just by measuring the force at which it yields. And how do you know it yields? Well, when it yields, you start with a nice straight bar that might be attached to a table here. What ends up happening is if you take that thing and reach the yield load, you'll absolutely know it. It will bend like that, and it won't come back. You've all seen that when bending paper clips and so forth. When it doesn't come back, you've hit the yield force. The stress it takes for yield you can also come up with by the dimensions of the bar and the force that is required. So you can again solve for the yield strength of the material. So you can measure all these things. This is good stuff you can do in the classroom. Density, stiffness, and strength can all be measured. And it turns out if you look at the properties of lightweight materials, it turns out density and elastic modulus hardly change with whatever alloy you're using within a particular alloy class. For steels, density is always about 7.9 grams per cc, and this should have units on it. Grams per cm cubed. My apologies for not doing that. Aluminum, about 1/3 the density of steel. Magnesium is lighter yet, and titanium is in here between aluminum and steel. And by the way, these are listed in sort of decreasing uses in cars. It's lots of steel out there, less aluminum, less yet magnesium, and almost no titanium in vehicles, and we'll see why in a little bit. Again, it turns out that the stiffness more or less scales with density. It doesn't have to be that way, but it about is. Steel has an elastic modulus about 200 gigapascals. Aluminum, it's about 73. Magnesium, about 44. Titanium, again, between steel and aluminum. And these properties, density and modulus, really depend on how atoms are bonded together at the atom scale. Strength, on the other hand, is dependent on crystal defects in a way we'll talk about later. Strength can vary all over the map. For steel, it can go from about 30 megapascals to about 2,000, seeing almost a factor of 100 in there on how strong steel can be depending on how you process it. Aluminum is very similar. It goes from very weak to very strong, usually not quite as strong as the strongest steels. Magnesium, again, you can have weak to strong, and titanium quite the same. Big ranges on strength, whereas again, density and modulus, very, very little within that. Relative cost, the reason we see a lot of steel in vehicles is it's the cheapest. Aluminum costs more. Magnesium is not necessarily a whole lot more than aluminum. It's a little more difficult to process sometimes. It's somewhat different properties. It can be a little more expensive. Titanium is actually quite expensive. That's the reason we don't see a whole lot of that in vehicles. So I want to sum up there. Properties and units are the key to design. Density and stiffness are controlled by atomic bonding. They don't vary much for a given material class. All aluminums have about the same density and stiffness. Strength and ductility vary all over the place depending on how the material was processed. And again, these properties can be described by units. Cost is another big variable we're not going to talk about today. And there's two parts to that. One is the cost of the material. The other is getting the shape and properties that you want. And we're going to leave those for another day. Look forward to talking to you later. Feel free to ping me with questions. Take care. Bye.